All right, rather than waiting for half of the class to show up, let's pick up from where we stopped. So one of the things I wanted to remind you is that as part of PCA, something you should always do is what is called widening of the data, which effectively means transforming the data to an uncorrelated form, because we saw that the covariance is equal to I, okay? I am going to need sort of to make a point on this transformation, and later on when we discuss independent component analysis, where I'm going to remind you that uncorrelated doesn't mean independent, okay? So this transformation makes the variables uncorrelated, and it is a step you should always do before you do PCA, but it doesn't mean the variable somehow became independent, something we will need on another application of these continuous latent variable models. Okay, there was an example in the notes that maybe we did, or you should read it. This is a standard data set for, it's a two-dimensional manifold, if I remember right. Yeah, two-dimensional manifold. The data are in, is it in 12 dimensions? Does it say something? Yep. No, 12 measurements. The original data are in what dimension? Well, it is on 12 dimensional space. Okay. Hopefully this is not a mistake. 12 and 12. All right. So this is something to test things, you know, and what you see here is the colors correspond to different regimes, to different classes in the data, right? And you want to effectively see how, if you project the data in principal directions, are these separation in classes actually obvious in latent space? And you can see sort of, more or less, you know, the colors have been separated, but not perfectly, all right? Is this the same color as that? It is, right? So obviously, you know, the separation there, okay, they're non-linearly separable, but you can see a lot of blue points that they are mixed with, what is that, orangey, green? Okay, with the green points. And the other thing I wanted to remind you as an example before we move on is somewhere when we discuss about classification, we introduce this Fisher linear discriminant method. I'm almost certain I did this, right? And anybody remembers what the idea was? So this was a supervised learning problem, right? We wanted to do classification. So we had labels for the data. So we knew that these points are blue and we knew that these points are green. So what was the idea in the Fisher linear discriminant method?
To maximize the criterion but model the separation between the groups.
So we maximize the separation. So you can see on this particular data set, right, the Fisher looks almost orthogonal to the first principal component of PCA. So in PCA, here you maximize this big overlap between the data and you maximize the variance. In the Fisher method, you maximize the separation of the data. So you have to be very careful when you use this type of things and what the objective is. Of course, in the PCA case, it's an unsupervised learning. In the Fisher linear discriminant case, it's a supervised problem. Okay, so we discussed the two very historical fundamental ways of introducing PCA. So let me finish this thing up and examine two cases. One case when the number of data is way less than the dimensionality of the problem, and another case when the number of data is way higher than the dimensionality. So if n is way less than d, so you can think d being 1,000,000 and you only have 1,000 data points, the only thing you have to keep in mind is the linear space where you can do PCA, the dimensionality, the maximum dimensionality you can have is n minus 1. Okay, n minus 1. So don't even bother to compute anything above that because all the eigenvalues of the sum of covariance matrix are going to come to be 0. And can you tell me why it's n minus 1 and not n?
Orthogonal.
I don't hear you.
Orthogonal.
Orthogonal. What is orthogonal? Okay, yeah, but why do I get n minus 1 and not n? When you compute the sample covariance matrix, have you done any pre-processing to the design metrics that somehow reduce the dimensionality of the problem? What have you done always? So you remove the mean, right? And that's 1 degree of freedom, and that's why only you can get up to n minus 1. So remember this, the rest of the eigenvalues are equal to 0. All right, so let's discuss another case that's very practical in certainly in engineering problems. When you do PCA in very high dimensional data, but so what we have is the case, so D is very high, all right? And so remind me, the sample covariance matrix, what's the dimensionality?
D square.
Say it again?
D square. D cross D.
So I have n data points of dimensionality D. What is the sample covariance dimensionality?
D cross
D
D.
cross
D.
D square.
D square.
Okay. What's the dimensionality? So let me think. What is, you look at X, right? Look at here. What's the dimensionality of this? All right, so it's D by D, okay, you're right. I was thinking something else. Obviously, I need to adjust my brain slowly. So the covariance matrix is D by D, and let's say D is 1,000,000, all right? But N is way less than D, okay? So doing an eigenvalue analysis and computing the eigenvalues and eigenvectors of this matrix will actually be extremely, complex. It will be something of the order really of D cubed. Okay, so can we do something actually that does not require computing the eigenvalues and eigenvectors of the sample covariance matrix? So again, N here is way less than D. All right, so what we do is we want to solve this eigenvalue problem, right? X transpose X ui over N, okay? Lambda I ui. So what I'm going to do is I'm going to multiply this matrix by X on both sides. Okay, there is nothing illegal about that. So I'm multiplying this with the design matrix. And now you notice, so what I do is when I multiply with X, this X ui I put inside parentheses and X ui I put inside parentheses. So effectively what I get is a new eigenvalue problem with the same really eigenvalues lambda I and eigenvectors that are X ui, so I call those VI. So the eigenvalue problem is written like this nice equation that you see on the middle. So what's the dimensionality now of X transpose? How much? N squared? All right? So which problem do you like to solve? Do you like to solve this eigenvalue problem, or you want to solve this eigenvalue problem? All right? So obviously you will solve this problem because of much less dimensionality. So N can be 1,000, but D can be 1,000,000. So you solve this, you normalize VI, all right? And then effectively what you need to do is, and by the way, again, this has only at most N minus 1 non-zero eigenvalues, all right? That's what you need to compute. And then if you have VI, you can actually compute UI from this equation, all right, by multiplying with X transpose, and UI comes to be equal to this nice form. Where do I get this factor here on the front? Right, so the X transpose V came from here. So where do you think I get the 1 over square root of N times lambda? I mean, when we solve the eigenvalue problem on the top, right, we assume, when we solve the eigenvalue problem here, we normalize VI, okay? So here, they are orthonormal. So what do you think this factor is doing here too? It does the same thing for the use, all right? So it normalizes the use, and you can actually test it All right, if you take UI transpose uj, you will see that this factor basically cancels out with, you will have to substitute on the top that lambda I is an eigenvalue of this type of problems. So bottom line, if you have a problem of high dimensionality, this is the eigenvalue problem to solve. All right, dimension n by n, you keep the non-zero eigenvalues and eigenvectors will be of order n minus 1. And then once you get v, you actually have u in place. And so this is very much advisable for many cases because many data are high dimensional, but you have very few of them. And I mentioned this is important in engineering because lots of problems in engineering, the data may be simulation data. So you have very few of them, but they are very high dimensionality. So you can think, this u and v being eigen functions of fluid flow or some electromagnetic field or things like that. So these ideas have been used. Lots of people make a living actually out of this for many years. And there are many, many versions of this type of techniques. I don't think you should use them today, right? Because they're extremely expensive. So these methods come with different names and, so it's good to know, right, that you don't have to solve an eigenvalue problem of dimension d by d. But again, this is still very expensive. All right, so let's move to probabilistic PCA. And I think we already discussed the fundamentals. So I am going to go a little bit fast until we reach the point where we have to train the system with maximum likelihood. So let me remind you what we have, right? So we have basically a generative model. Z is the latent space, obviously of reduced dimensionality. So we put some prior that it's trivial, looks like this in this case. We discussed that if you try to make it more general, it makes no difference. The key thing here is for this probabilistic PCA, this prior is Gaussian. That's what you need to remember. If it is not Gaussian, things basically, you get lots of other interesting things. So P of Z looks like that. And then we introduce a generative model that tells me how from reduced dimension Z, I can go to high dimensions. And I do this with a linear model. So the mean, it is Gaussian, is WZ plus mu. Obviously, W has dimensionality of D times M. Let's call M the dimension of Z, okay? And we take an isotropic covariance. If you make this a very general diagonal matrix, you basically get a probabilistic version of the factor analysis. Really, there's no complication in doing that. Just, when you look at this slide, these equations that we have seen, we see here, these two equations, they are really defining a naive Bayes model the way we have seen it, because given Z, the X components are independent. All right, so really this is a nice application of naive Bayes type of model, which means it's not very sophisticated, right? That's why we call it naive. Okay, so given Z, these X's are independent. All right, so we can write this model, if we remove the Gaussians, as X equal WZ plus mu plus some Gaussian noise that looks like this, or as I mentioned, you can take it any general diagonal matrix and you get factor analysis. So I'm going to use this equation explicitly like that as well. So pictorially, you can think if X is a two-dimensional vector and Z, so you do dimensionality reduction down to one dimension. P of Z is a nice Gaussian. So you sample Z, and for each sample Z, you have to compute a Gaussian that is centered around WZ plus mu. So mu plus WZ, and then you put some isotropic noise around. So that's the distribution P of X given that Z. Key thing here is this generative model, right? It allows you to generate X's by sampling in the reduced latent space Z. So this is sort of your new way of looking at dimensionality reduction. We don't simply say, oh, I have this data, can you reduce them to one-dimensional data? Yes, we will do that, but we do it in a generative way that also allows us to go from z to x through this equation or through this generative model that you see on the bottom. Now, if you take this generative model, you multiply with this prior model, and you integrate z out, right? You have the product of two Gaussians, and you integrate them out. This is a linear in z. You can actually show from the linear Gaussian models that P of x is WW transpose plus sigma square I. So you may say, okay, I did all this analysis, but my P of x is a Gaussian, so what have I learned? I don't see any complexity in the model because the data that I generate are, coming from a Gaussian. So why not, if you emphasize the generative aspect, why not just put a multivariate here, Gaussian, and sample from it? Well, the answer to that is that if you have a multivariate Gaussian in d dimensions, the covariance will be of the order of d squared. And here, what's the order of WW transpose? Remember, here x has dimensionality d, all right? And z has dimensionality m. So what is WW transpose? D cross D. So what have we, so if this is okay, so obviously this has to be d squared, right? Because x lives in dimensions d. But what is the cost of computing this covariance there? I mean, what do you need to evaluate? So a general covariance, if you have a general covariance matrix here, would be d squared, okay? So here, what do we need to evaluate this? We need to specify sigma squared, so one variable, and W, how many variables is W? D times m. So we go basically from d squared to d times m, and that's where the idea of Cont reduction comes, right? So really what we have here is we try to reduce the complexity of a multivariate Gaussian through this reduced model to something that the covariance has less parameters than d squared, and in this particular case, it's really d times m plus 1. So if m is way less than d, the savings are significant, but don't forget, this looks a simple model, all right? It's not very sophisticated yet. Okay, this is a trivial derivation of this equation, so I'm not going to go through this. So if you don't like to use equations of linear models, you can use that x is equal to wg plus mu plus epsilon, and that P of x is Gaussian. You can compute the mean and the variance, so rather straightforward. All right, and I mentioned if you generalize the prior on z, it makes no difference because with some transformation of mu and w, you can get back the previous form, so there is really no gains there. All right, here's a problem we have. Obviously, if we're going to do maximum likelihood, right, or some other way to calculate w and sigma squared, we are going to have to ask, is w unique? And the answer, unfortunately, is no, it's not unique, because if you rotate w, in principle, that means if you rotate the latent space, because w operates on the latent space, so if you rotate w by w times r, where r is some orthogonal metrics, you can see the new WW transpose is the original WW transpose. So if you do optimization to calculate W, which W are you computing, right? There is a missing rotation there, so which W are you going to be computing? So in principle, there is nothing you can do about this, right? So that rotation cannot be calculated, okay? So there are tricks. You can say, I'm going to fix the rotation, or I'm going to do some gradient optimization, start with some initial guess of W, and whatever I get corresponding to some rotation, this is what I have. But bottom line, you cannot identify this rotation R that you see there. All right, So we have WW transpose plus sigma squared I, all right? Now, this matrix here is rank deficient, right? So you need to be smart. I mean, it looks like it has dimensionality d by d, as you told me, but when you invert, you should be able actually to invert this matrix at the cost of inverting an m by m matrix, right? Because W itself there, right, has dimensionality d times m. So you need to take advantage of that. And how do you take advantage of that? You remember in very early lectures I told you about the Woodbury Formula? You remember the famous Woodbury Formula? So here is the Woodbury Formula in action, okay? If you call this covariance matrix C inverse, WW transpose plus sigma squared I inverse, you get this, where the only matrix that you need to invert is the matrix M, and M is not W transpose, it's W transpose W plus sigma squared. Okay, nice. So basically, you go from the inversion of something that is d by d to something that is m by m. So the computational cost for the eigenvalue problem basically is reduced from, and the inversion, it is reduced from d cubed to m cubed. All right, so significant advantage. Now, if you don't remember anything about the Woodbury Formula, the nice thing is when you have slides, you can cut and paste them from one lecture to another. So here is a reminder of the Woodbury Identity, and you can consult it and substitute the right symbols here. All right, use your imagination, what corresponds to what, and then you get a nice formula that I showed you before. All right, you can actually use these equations for linear systems and compute the projection of a high dimensional data X to the latent space Z. So you can actually, so you remember we used to have P of Z, and we used to have P of X given Z. So now you can use Bayes' rule, and you can compute P of Z given X. You don't really need to do Bayes' rule because we already have done it. So what you see on the bottom are the very general results for doing this inversion for Gaussian linear systems. So if you remember these formulas, and again I cut it and paste them from another lecture, you can reinterpret. So when you look at these formulas, right, don't say what is Y, what is, you know, these are generic formulas, so you can reinterpret. So for example, this X here would be our Z, this Y would be our X. Okay, so you can reinterpret this and you can get this projection, and so you get this mean, and obviously there is some uncertainty involved with the projection as well, which is nice, okay? So generally speaking, if you want to, if I give you some high dimensional X, right, and you want to find some reduced representation, maybe the easiest thing to do is report the mean, right, which is m minus 1 W transpose X minus M. If you want to do beyond that, you can report the mean, and around it you can put some contours of the Gaussian with covariance sigma squared n minus 1. So we need to do some estimation now of W and sigma squared. All right. So you remember if we integrate Z out, this is the covariance we get. And so we're going to compute the log likelihood. So we're going to assume that we have capital N data points Xn. So capital X is all my data points, right? One row is every data point. So capital X is N times D, okay? So the log likelihood would look like this. Summations of the logs of these Gaussians. And if you expand it, you get something like that. Let me see what's on the top. So we actually get this nice formula on the middle, where I have used a very famous trick here that maybe I already mentioned to you in an earlier lecture. So what's the trick that I used on the last term, which is very standard trick, used every time. This last term here, right, is a scalar. X transpose some matrix times X. And because it's a scalar, I can write a scalar equal to the trace of a scalar. And when you have the trace of ABC, you can permute the symbols around and get the same answer. So what I have done is I took this, if I write this equal to this trace, I put this X transpose on the other side, and then what I get is C minus 1, and I pull the summation inside with a factor 1 over n and n there, and I get the trace of C minus 1 S, where S is the sample covariance. Okay? Everybody can see this? This is, every time you have this, that's the trick, okay? That's the way to get basically the sample covariance to come in the picture. Okay, so the model basically that we need to maximize this log likelihood, and the unknowns, of course, is W that's coming inside C, and what happened to the noise sigma square? Where is sigma square coming in? Sigma square also comes in C, right? You remember in C involves plus sigma square I, okay? So we need C involves both W and sigma square, so we have to compute those things. So the proof is actually not very complicated, okay? But there is some trivial algebra we have done many MLE problems. So you can click this. It's a very small paper, and you can actually see formally the analytical results for the MLE estimation. So I'm going to give you what the results look like. So first, the W comes to be U times L minus sigma square I to the power 1/2 times a rotation R. We'll start with the rotation. The rotation is arbitrary, so not surprised there. L is an m by m diagonal matrix that involves the eigenvalues of the sample covariance matrix. So basically, things here are scaled with this factor scale lambda I minus sigma square. And UM is a matrix that contains the m leading eigenvectors of the sample covariance matrix. I mean, not surprising, right? So basically, you remember when we did PCA, all right? What was the principal subspace in PCA, in standard PCA? Where we were doing the projections in standard PCA? The eigenvectors of the sample covariance matrix. So here, what we get is, really, what is W, right? W is the matrix that takes us from latent space to physical space, the high dimensional space, right? This is how we do the projections. So it's not surprising that this matrix U there comes to be the m leading eigenvectors of the sample covariance matrix, but you can see in the general formula for W, this is scaled with these eigenvalues, lambda I minus sigma square, okay? So obviously we will need this because the model is probabilistic now, so we need something new is going to come out basically from this analysis, okay? And so this, there is a U there, but there is some other terms, and of course the model is able to tell you there is a rotation there that's arbitrary. And is there any formula for sigma squared that you get with MLE? Yes. And look at that not surprising result. So sigma squared comes to be the average of the discarded eigenvalues. Where did we see these discarded eigenvalues? Say it again? Distortion? Oh, in the distortion criterion. So tell me more about the distortion. So in one of the, so we did two formulations, right? One to maximize the variance of the projected data, another one to minimize the errors. And we computed that the summation of these eigenvalues, right, does what? There was no probabilistic interpretation, right? But what did we tried to do what to the variance? So the distortion criterion that you mentioned, what was the distortion criterion with words that led us to this summation of the discarded eigenvalues? So we were trying to do what? To maximize the variance of the projected data. All right, so that's the criterion. So the summation of this lambda I is what? Or even if you see it, if you project, let's say the data to this principal subspace, then we have everything else is normal to that subspace. So this is basically the error that you do in the approximation, right? Using the latent representations, the projected points basically, in both criteria. So here, it comes out now that this summation is related with the noise that you get in the probabilistic version of PCA. All right? So sigma squared comes to be 1 over the average, basically, of the discarded eigenvalues. All right? Let's do a few simple calculations to see the meaning of these equations, right? So I remind you, so you remember our predictive distribution had a mean mu. This is actually, I should use the Greek mu here, and this was the covariance matrix. So I remind you, if you want to compute for this distribution, you want to compute the variance in any direction v, the variance is v transpose cv. So what I want to do is I want to compute the variance in directions that they are in the principal subspace and orthogonal to the principal subspace to see what type of calculations, what type of results this model gives me. So what I'm going to do is first, I'm going to take a vector v that is orthogonal to the first m leading eigenvectors. All right? So if you calculate the variance in that direction, so again, this is a direction orthogonal to the principal subspace. So you have v transpose times c, which is w transpose plus sigma squared I v. Will you trust me without plugging in anything here that this times this will give me 0? From where is that going to come? Why v transpose w transpose v is going to be 0 for this? Because remind me, what is w? The optimal w that we computed with MLE? It was the scaling of which matrix? What is w? What is the w that we computed when we do maximal likelihood? It was on the previous slide. So what is w? What's the first term in w? Say it again, it's u. So when you take u, don't forget, contains which eigenvectors? The first term leading eigenvectors, but v is orthogonal to them. So can you see that v transpose w and w transpose v will come to 0? Yes? All right? So the variance, it comes out that the variance in every direction that is orthogonal to the principal subspace is actually sigma squared. It's the same. All right? So the variance in every direction of the orthogonal to the principal subspace is sigma squared. All right? If this was the correct, let's say we do model reduction, right, and we keep the m leading eigenvectors. If this result was going to give you the right answer, what would be the right answer there? Let's say if this was v was the m plus 1 eigenvector, what would be the right answer, the exact variance? If it was going to give you the exact, we were not using this approximation, and it was going to give you, if we do the eigen, we compute the exact, all the eigenvalues and eigenvectors, all right? What would be the exact variance for the m plus 1 direction? That eigenvalue, lambda m plus 1. So which means that this model basically loses variance, right? It doesn't model the variance correctly in the directions that they are orthogonal to the principal subspace, okay? So that concept of the summation of the extra eigenvalues, right, being the variance that you don't capture, it also comes here because actually what this model does, it gives you that the variance is constant. It's equal to sigma square in all orthogonal directions to U. Now, it comes out not by accident. If you take a direction UI that is in the orthogonal subspace from 1 to M, and you plug it in there, and you put W to be equal to this, this times that, you remember the scaling here on W, right? The scaling on W was this matrix, diagonal matrix to 1/2. So you're going to get twice that problem. So you're going to get lambda I minus sigma square plus sigma square, which is lambda I. And that means that you actually capture the variance precisely, correctly, in the every direction in the principal subspace from U1 to UM, okay? So, so now you may want to appreciate basically that, you know, this decomposition and this scaling that comes here, all right? Because this is actually very much captures the variance that you represent in its principal direction or direction orthogonal to the principal axis. Okay. All right. Now, again, there is nothing you can do with R, right? But I am going to show you, hopefully today, that if you try to do this MLE problem using expectation maximization, right? Remember, the expectation maximization is the standard way to do maximum likelihood, okay? In many, many different settings. So if you do expectation maximization because it's an optimization problem, you will start with some values, let's say, of W and sigma square. Eventually, you're not going to have any ambiguity in EM in the context of R, because the algorithm will converge to some local optimum, okay? And so in some sense, the algorithm will be setting for you what that R is, so you will not have to worry. But it doesn't mean that there is an optimal R. So if you restart the algorithm and you do it again, you will get a different answer. All right. This doesn't say anything. It says basically that if you have no dimensionality reduction, the matrix C comes to be equal to the sample covariance. So you get back to the original problem, so there's nothing new. Okay, implementation of this, and this is very actually tricky, because if you try to put in the computer formulas the way that you see them in books, you will not be able to do any large-scale problems. So obviously, you're going to have to compute the inverse of the covariance matrix of the predicted distribution P of x. And using the Woodbury formula, right, we said that C inverse is given by that nice formula. So with some rewriting, nothing major, all right? Some rewriting, the way you're going to implement this inverse is very simple. You have to compute the M leading eigenvectors. This is the matrix UM. And then this is a diagonal matrix that is 1 minus sigma square divided by lambda j, all right? So this has the M, only the M leading eigenvectors, eigenvalues lambda, okay? And then, you know, what else you will need to do is you will need to calculate the determinant of C as well. And the determinant of C, I shall give it to you as an you know, in-class exam problem. The determinant of C is given by this nice formula. Okay? And you see the merit of actually writing things by hand. When you look at that formula, you say, I cannot be right. So what you do in life is when you derive that formula once, you write it, you put it in the slide, so the next time somebody asks you to derive it, you say it's there. Okay? Because you would otherwise it would take you half an hour to do it. So the determinant of C, you actually have to use the matrix inversion lemma that gives you this very nice, you know, this is part of the Woodbury formula type of calculations that we have seen before. So if you want to calculate the determinant of A plus UW V transpose, okay, you can actually write it with this nice formula here. It's the determinant lemma, basically. And so if you substitute, you plug in what W is in here, and you have to compute this determinant. This thing inside the determinant, you can write it in this form, okay? And you can expand it. You can actually go home and say, this is equal to that, this is equal to that, etc. But this is what you get. This is a diagonal matrix because there is a U transpose U. So this in the diagonal has 1 over lambda I minus sigma square, and there is plus 1 over sigma square, all right? And that gives you, so 1 over lambda minus sigma square and 1 over sigma square. It gives you lambda I divided by lambda I minus sigma square. And then, you know, that term will give you this big parenthesis, plus from there, and this is your nice formula. So can you imagine, right, that you don't do this calculation by hand, and because you're going to need, you know, in the covariance matrix, you need the determinant of C, you go and you say to the computer, oh, compute me the determinant of this matrix million by million. No, you don't have to do this because here is a very nice expression knowing that W is basically of dimensionality D by M, so you only need the M leading eigenvalues to do the calculation. So the program that Murphy has, that I think you will use in the homework, I believe it uses precisely this formula to invert C and calculate the determinant of C. All right. I'm going to bypass this. There's nothing there. Can you tell me, so, you know, when you do, you know, when you project X basically to the latent space Z, I wrote before this distribution of Z given X, and we said basically if you take the mean, all right, this is what you get, okay? And this is the variance. And actually, you know, you can go backwards. If you have, so you have calculated the projection of X back to Z. You know what is this? This is the reconstructed X. So it's like you encode X to a low dimensional space, and when you need X, is that. Because you remember what is X? X is W times Z plus mu plus some noise, so the mean is really that. Okay, so this is like an you know, autoencoder, if you like. You go down to Z, and then from Z you can go back to X. And so I'm not going to go through the details of the slides. Can you tell me what do you think is going to be happening to all of these formulas when the noise sigma squared goes to 0? I mean, we tried to do probabilistic modeling, right? We said this is a Gaussian distribution, the probability of X given Z. We put some noise sigma squared. So what will happen if the noise doesn't exist? It's going to 0. What do you think, when you take all of these formulas, what do you think they're going to give you? Or what they should better give you? The regular PCA, thank you. So, so basically when you take, who was that nice voice? All right. That was a baritone voice. All right, so when you do this, you get a regular PCA. All right. So what's the difference of probabilistic PCA from regular PCA? And so in regular PCA, right, you, if this is, let's say, if we look projection on this line, that's the first principal component, if you like. This is the mean, right? Is this at 0, 0, right? I cannot see it. Yeah, this is at 0, 0. So this is the mean, basically, of the data, okay? So the projections, basically, that you will have are orthogonal, right? That's what PCA is. You take the orthogonal projections to the principal subspace. When you do probabilistic PCA, actually, the projections that you see here are not orthogonal. They are all shrinking towards the mean that you see with this star there. And that's the major difference between probabilistic and regular PCA. In some sense, the probabilistic PCA, right, does this generic shrinkage that acts as a regularization process that we have seen in many different settings. So these projections that you see here are not orthogonal, all right? So don't affiliate in your mind that somehow PCA is you take the projection, so that's the best approximation you can do. No, in a probabilistic way, these orthogonal projections, you'll be better off if you shrink them towards the mean, which is represented here with a star. Okay. So can we do expectation maximization for this problem? So can someone in a few lines tell me what's expectation maximization so we can see how we can apply it? I mean, I was hoping that some of you in your projects will pick up nice things like doing EM for this mixture of that and that model and that. And I've seen some weird projects, right? But applying EM to interesting problems is very nice because EM is universal. So if you understand EM for one problem, you can do lots of different things. So what is EM? What's the whole idea of EM? What do we have to do mathematically? What is the E step? What's the M step?
Find the expected values of the latent variables.
So in the E step, find what?
The expected value of the latent variables.
All right. So so the expected value when because that expected value was the same as the posterior probability because we used with discrete variables, right? For sure, in the first step, we have to calculate the posterior of the hidden variables, of the latent variables. All right? And in the M step, we have to compute what? Formulate the joint log likelihood of both observed variables and latent variables, and then take the expectation of this with respect to the posterior that we got on the E step. And then on that expected joint log likelihood, do what? Maximize with respect to the parameters. So in the context of PCA, can you tell me what are the observable variables? Well, it's my data X. What are the latent variables? Z, the projection Z. That's the latent. For every X, there is a Z. So on the first step, then, we will have to calculate the posterior of Z given X. Do we have the posterior of Z given X in PCA? In probabilistic PCA, do we have the posterior of Z given X? Yes? It's there. So then the only thing, so we know what the mean is, we know the covariance. So the only thing we need to do is write down then the expected joint log likelihood and do the optimization of that with respect to W and with respect to sigma square. So let me show you the algebra. This is the joint log likelihood of X and Z, all right? We know this Gaussian from the generative model. We know this Gaussian from the prior model. So that's the joint log likelihood. Okay, these are the formulas. There's nothing there. And now we need to be able to calculate the expectation of the joint log likelihood with respect to the posterior of the Z variables. So everywhere we have Z's, I put the posterior, so I expand this log likelihood, right? All the terms that you get here are coming from expanding this, right? And expanding that with that. So there's now fancy calculations. But everywhere I have Z and Z transpose, I need to take expectations. So here I have the expectation of Z. Do I know what the expectation of Z is? Of course I do. Do I know what's the expectation of Z transpose? Of course. It's the covariance, right? Plus E of Z times E of Z transpose. Yes? Everybody with me? All right, so obviously here there are parameters involved, right, sigma and m, but since we're going to do this iteratively, all right, so in the first step where you will calculate this posterior expectations, you know, this sufficient statistics, if you like, you will keep the parameter sigma squared and m fixed, and then you compute this, and then when you compute this, you will go and maximize now with respect to sigma squared and W transpose. Okay? So again, keep in mind, it's not written explicitly in the slides, right? Inside these expectations, the parameters are the old parameters. So when I write this, I should put everywhere sigma squared old, you know, M all inverse, etc. But the rest, M, sigma square, are the parameters we need to update. So when you plug in your sufficient statistics, you go and take derivatives with respect to W, you set it equal to 0, derivative with respect to sigma square equal to 0, you get analytical formulas, and this is basically the formula for W. This is the formula for sigma square, okay? And obviously, they look very, very different from what we did with the exact, MLE estimate that you saw before. But somehow, you have to trust me that these formulas, in the case of sigma square going to 0, they also converge to what? To the exact PCA results. Because if they don't, we have a problem. But if sigma square is not 0, these things will convert to some local, right? Since we work with log-like with some local maximum, but there is no a local maximum there, okay? Because of that rotation involved. So here you will get one solution when you do expectation maximization. In the probabilistic version before, there was this uncertainty with the rotation that doesn't come up in this picture. If you actually study these formulas carefully, you will see that you gain a lot of things when you do expectation maximization, because the cost can be substantially less than using the exact formulas that we showed before. And the reason for that is if you have a lot of data points, or if the data points come one at a time, what actually you can do, you can compute the sufficient statistics one data point at a time. All right, so you can write this in an incremental form, and doing even the inversions, you see all the calculations here in an incremental forms, and I think that's the best way to actually program this, to implement the EM algorithm. The proofs are actually the slides, but it's just simple algebra, okay? And all right, so we don't need this, we don't need that. Don't need this, we don't need that. So let me, I'm going to show you the expectation maximization algorithm in practice, all right? So we only do here a one dimension. So basically we project two-dimensional points on this line, all right? We have iterations of the EM steps, right? So can you tell me what step we're doing here? So we have the data point, we remove the means and all of these things, right? We did what we're supposed to do with regular PCA. So what is the first step here that you see pictorially? What exactly are we doing? I mean, from what I see there, right, it looks to me like orthogonal projections. What exactly are we computing on this step? On this step, you told me we compute the posterior of z given x, right? And we had that analytic formula from probabilistic PCA to do that. The projections that we see here are orthogonal because the subspace remains fixed in the analysis. Okay? All right? So what do we do in C? So in C, with this posterior of the z fixed now, which means this points on the subspace fixed, what is changing? I mean, I'm projecting on this plane, right? But what I'm doing on the M step? I'm going to have to recalculate W, and in this case, W is the slope of the principal subspace where I do the projections. So you can see now, it's like, you have all these points attached to the subspace, and the subspace moves up or down, right, as you optimize, and the projections are not anymore orthogonal. Very similar to what we got with PCA, right, for probabilistic PCA, where we effectively said that the points are shrunk towards the mean, and that's, again, what happens at the end of the M step. And of course, now for that new subspace, you update the projections, you update the subspace, and eventually, basically, you converge, and things will look that they're orthogonal, etc. But in the iterative process, I mean, we stop here at this step, right? Because there's no any more update that we can do on W. So there's lots of different programs actually that you can use for your homework. All right. So this is again, this program is from Murphy's book. You can see this thing, and let me see if I wanted to tell you something here. Here there is actually, if you are interested, in the case where, does it say somewhere sigma squared equal to 0? Well, it obviously says something. If you take any of the, like the EM version or the generic probabilistic version, right, and you take sigma squared equal to 0, you can actually show at the end of the day that the problem, it's actually identical to a least squares optimization problem. So effectively, if you don't have any noise and you pose the problem of projecting high dimensional data X to some latent space Z, you can say, let me define an approximation that looks like this, right? So if I project Xn to mu plus Wzn, that's the error that I do. So if I minimize that the way we did it, right? That would be optimal in this L2 sense. So it comes out that when you do this classical regression problem, if you like, the results that you get with no noise are identical to what you get with the EM algorithm as well as the probabilistic PCA algorithm that I showed you before. I mean, it's nice that the formulas basically agree, even though they look very different. In the case of sigma squared going to 0, all the formulas, if you check them carefully, and I have the details on the slides, they give you the same answers. All right. All right. So I have only 15 minutes, right? And so I need to sort of give you only the essence of some of the remaining lectures. So maybe we can start another topic tomorrow. So if you are interested, there is a link under this on Wikipedia that in extremely readable format, even though there are some typos I noticed last night, in extremely readable form, you can read about what's called independent component analysis. So let me define what the problem is. So suppose that two of you in the back of the room, right, talk, and I have two microphones at the end of the room, and they are picking up basically an average of the two signals from you. Okay, so the problem that we have to define here is the following. If we measure the mixture of the signals Z1 and Z2, can we actually go and recover the original source? The original sources Z1 to Z2 at all given times, right? Not only that, but can we also recover the mixing coefficients W? So again, imagine Z1 and Z2 are your voice signals coming from two different sources, two different students in the room, and I have two microphones that pick up an average of the signal X1 and X2, and I want to, given X1 and X2, I want to compute not only the original signals C1 and C2, but I also want to compute the mixing matrix W. Okay? So a very practical problem. And to make life easy, I'm going to discuss one of the methodologies for addressing this problem. I am going to do this for one time. Okay? So we are not going to bother about the time there. And I am going to assume here that the signals that I measure are in number the same as the sources that I try to identify. All right? So obviously, if you have more x's than z, you can still do the problem with no difficulty, but right now I am going to take that they're equal. So in this case, 2 and 2. Now, does this problem look like PCA in an abstract way? And you know, don't bother with the fact that this is two-dimensional and my z's are two-dimensional, right? As I said, this can be way higher dimensional than the z's. But does this look at all like PCA? What are the commonalities with PCA looking at this problem? If so here we want to identify the sources of this z's play what role in PCA? The latent space, the reduced space, okay? Now they have physical meaning. They're not just abstract entities. They are what it generates, basically, the signals x1 and x2 that I measure. So z is the latent space, okay? That's the commonality. So we want given x to, so we want given this to compute the latent representation. Now, if you think of this problem as a PCA, right? And so remember in PCA what we did is we put a Gaussian model on the latent z's, right? And then we put a generative model that takes us from z to x, which was also a Gaussian. And what was, you know, I want you to think about, if I approach this problem as a PCA problem and I try to estimate z given x's, is there any issue that we're going to have to basically give up with the PCA methodology that somehow will not allow us to proceed here? So you remember here I'm asking to uniquely identify, to whatever possible extent, z1 and z2 given x1 and x2. So can you uniquely identify the latent representation in PCA? Given x, can you identify what z is? What was the deficiency, the issue with PCA, that it was a hanging on the air that would not allow us to compute everything the way we wanted? What was that? Say it again?
The second term in this expression.
The second term, which second term?
W1, 2.
No, I mean, this is like a w times a vector z, right? Exactly as before. If you write this as a vector, x equal wz, and I don't have any noise here. You can add noise as well. I have x equal wz. If I try to do an inversion in the PCA way and say, find what z is given x, what is in PCA that will not allow us to answer that question? Remember, the PCA results were identical and invariant even when I was doing rotation in what space? In the latent space. All right? So basically, because when you do PCA, you can find z, you can find the principal subspace up to a rotation. All right? So we will not be able to uniquely identify z because the principal subspace is computed up to a rotation. So how do we solve this problem? Well, here's the idea. And it's very natural and very practical, actually. The source is z1 and z2, right? Two of you speaking at two different parts of the room. They're very independent of each other. All right? So the sources are very independent. And the other thing we need to do is we need to assume that the prior distribution of the z's is anything but Gaussian. All right? So let me remind you, because I said it today when we started in the lecture, we said that if you have, let's say, you remember on my first slide on the lecture today, I started with data x, and then we did widening. And we transformed, you know, as a pre-processing to y, and we said that the widened data are what data? Uncorrelated. But uncorrelated does not mean independent. All right, so effectively, PCA can give you, with the widening transformation, uncorrelated data, but it cannot give you independent data. So what we need to do is we need to produce independent data here. And the way we're going to do this is by assuming, so the z's are independent, and the distributions for the sources P of z are non-Gaussian. All right, so as I said, that I need to bypass lots of things for you. So let me see if I can go first to slide 132. All right, so even if, so we're going to assume that the z's are jointly independent, but still there is an issue, all right? And there is nothing you can do about this issue. So issue one, if there are two students, will I be able to identify that student one is this person and student two is that? No. And you can see here, if you take a permutation of the z's, you basically get the same answers, where the w is basically changing by permutation, another permutation for the z, and the same thing if I actually do any arbitrary scaling of the signals. So you know, I will be able to compute the signal as a vector, but I will not be able to identify the magnitude properly, because you can see here, you can put any scaling on z, and you can modify the w accordingly, and that still is a solution. So we will solve the rotation problem, but this non-uniqueness in the context of permutation, sign and scale basically will not be resolved even on what we call independent component analysis. All right, so let me make some assumptions. We're going to assume that the mean of z is 0, and it actually doesn't matter. You can generalize this very easily, and we're going to assume that the covariance of z is I. All right. So we're going to assume that the data X, the signals, the mixed signals that I have given you, they're widened, all right, with PCA. So we are going, so E of X will be 0, and E of X transpose equal to I. So the data X that I give you are uncorrelated. We can do this with regular PCA, all right? So if you compute the covariance of X, right, and X is W times Z, and we already have assumed that this is equal to I, you can immediately see that this W matrix is orthogonal, okay? So from this calculation here, with the assumptions that the data X are widened, and then the assumption on Z, as I told you, a similar assumption for Z, means that W is an orthogonal matrix. Okay. So let me, I'm going to jump directly to one of the techniques, basically, that will allow us to compute W. And actually, in particular, I'm going to compute the inverse of W, which I call matrix V. So the transformation is X equal W times Z. All right? So if I use the probability transformation law, will you agree with me that the probability of X computed at X is WZ is the probability of Z times the determinant of W inverse? You remember how you transform probabilities, right? X is equal to WZ. So can I write this equal to that times that? All right. This is the probability of the sources, and we will discuss what choices you have for this. And we said we're going to denote W inverse to be V. So this is the determinant of V. So I have given you a bunch of data X. So there is a log likelihood, and I assume here that I have T data. So I divide my log likelihood by the total number of data. So I'm going to have, when you take logs, and you're going to have T of these determinants divided by T, I get that. And then I have summation over the T's of log of Pj, all right? What is Z? Z is W inverse, which is V, so it's V transpose X. So I want you to look at this now. Here I have written this distribution over summation for all the components of Z. What assumption have I made that allowed me to do this substitution? So here I have, right, I'm trying to write the log of this term, and Z is V transpose X, and I write V transpose X as the summation of these logs where Vj is the jth row of this matrix V. What assumption allows me to take V times X and write the distribution of V times X as the summation of this distribution over these row vectors times xt? I mean, this gives me basically the distribution of Z, but what assumption I do in Z that allows me to write this as the log probability of the first component, the log probability of the second, the log probability of the third? What assumption allows me to do that? Independence. Okay? So effectively what we have is the independence of the Z allows me to do like this, all right? So if you actually, since you have samples over T, all right, there is no dependence. So this is orthogonal matrix actually too, because W is orthogonal, so this doesn't contribute anything in the calculation. So I have 1 over T times this summation. And you know what? Can I write this as an expectation? 1 over T times summation of all the data points. I can write this as an expectation using Monte Carlo. And I'm going to set, this is the log of Pj evaluated at Vj transpose xt. I'm going to introduce the minus log of the source probability, all right? And I call this Gj. So effectively, I need to minimize the negative log likelihood, that is summation over all the components of the expectation of this minus log of the source terms. Okay? I know there is a lot of there, right? But effectively, the only thing I want to emphasize here is we have done nothing else but write the likelihood, and the likelihood is in terms of data X, but I express it eventually in terms of the distribution of the sources, right? That's the idea here. In terms of the distribution of the sources, and I use an independence assumption that tells me that each component in the sources is independent, and somehow the problem becomes one of minimizing the summation over each component of the expectation of Gj, where Gj is minus log of the source probabilities. So effectively, we can do stochastic optimization and compute each row in the matrix V, right? These are the inverse of the mixing coefficients, if you like. So we can calculate each row in the mixing coefficients using minimization of this, all right? And the only thing that you need to be concerned is what distribution should you use for the source distribution? And there is a lot of discussion in the slides. So bottom line, you should use anything that looks as far away from Gaussian as possible. And that's all. And you will have two choices. You can go actually and optimize this for each Vj alone. So update the first row of the matrix, the second, etc. Or even better, do the stochastic optimization and update all the rows simultaneously. And actually what I have in this slide, and we will finish with this because 144, what I have done is I have written the objective function that we want to minimize. And you notice I put a Lagrange multiplier for V to enforce that V has magnitude 1. And I'm going to use a Newton method, which means I need to calculate the gradient, okay? And so little g is the derivative of capital G, all right? So remember, this comes from the distribution of these source signals. And you need to compute the Hessian. There is a little assumption that I make in the Hessian. You can question it, but somehow this leads to identical results with many other methodologies. And then what you need to do is you need to apply the Newton's update, where you say the new values of V is the previous Hessian inverse times the gradient. And the update formula looks basically a simple formula like this. It doesn't tell you what the magnitude is correctly. It tells you what the orientation is. And you can keep iterating this algorithm and compute V. So independent component analysis has, there are books written on the subject. lots of applications, but really sort of mathematically, all of the techniques that exist out there in the literature for computing these vectors V, if you like, they all more or less give you the same answers. So what we have done here is, right, we use mainly the independence assumption of the source signals. If actually you don't use the independence assumption, but you use, tell me one way to enforce independence. Here we did it explicitly. What would be a nice way to enforce independence of the components of a vector Z? Something else that we had mentioned once. How do you enforce? What's a nice criterion to say P of Z is equal to P of Z1 times P of Z2 times P of how many signals you have? What is that thing? If I take the KL distance of that, how do we call that? What's the KL distance of P of Z and from P of Z1, P of Z2, et cetera, et cetera? Mutual information. Okay? So if you actually set it before the light goes off, if you set the minimization problem in terms of mutual information or in terms of maximizing entropy, etc., all of them give you the same results as the ones I showed you before. So you can read on the slides, but actually after you finish reading them, you say, but the answer looks identical, so what have I learned? What you have learned is independence is key criterion here in the